So in earlier lectures, we have seen what is a uniaxial stress state, what are biaxial stress state. Today, so we now will be looking at what are 3D stress state and how to find out what are principal stresses in 3D. So let me write it down first. So we have studied uniaxial stress state, that is like uniaxial tensile test in that. So it is also called as 1D stress state. Then we have biaxial stress state, that is 2D or plane stress, and we now will be dealing with triaxial stress state or 3D. So let me take a point O and let me draw my axis as x1, x2 and x3, and let me take what are the stresses acting along sigma 1, sigma 2 and sigma 3. So in triaxial stress state, you'll have sigma 1 equal to sigma 2 equal to sigma 3. Let's say I will not put it as equal, but it will be non-zero. Okay, so all these stresses will be not equal and they will be non-zero. So that is my triaxial stress state. So similarly, I can write it for, let me write it down for uniaxial stress states. You will have only sigma 1, sigma 2 equal to sigma 3 equal to 0, and biaxial stress state you have sigma 1 not equal to sigma 2 and sigma 3 equal to 0. So we have seen this. In triaxial stress state, you will have some two special conditions which I would like to mention it over here. It is like when you have sigma 1 equal to sigma 2 equal to sigma 3 equal to sigma, so I call it as hydrostatic stress state. Hydrostatic. Or when sigma 1 equal to sigma 2 not equal to sigma 3, I call it as cylindrical stress state. Now let me take my stress tensor. I have mentioned it over here, which has 9 components, and out of which only 6 are independent. Why the 6 only are independent? Because our stress tensor is symmetric. Why it becomes symmetric? Because we put a static equilibrium condition, and then we can find out that sigma 1 2 must be equal to sigma 2 1, sigma 1 3 must be equal to sigma 3 1, and sigma 2 3 must be equal to sigma 3 2. That is why we only get 6 independent components of stress tensor. Now let's consider a 3D stress state. Let me consider a point O, and let me mark my coordinate axis as x1, x2, x3. Let me put one plane ABC, and I call it this plane as my principal plane. So what does principal plane means? There will not be any shear stresses acting on this plane, and there will be a normal stress which is acting on this plane only. So we will not have any shear stress and only normal stress. That normal stress is nothing but your principal stress. Let me call it as sigma. So the sigma is my principal stress and ABC is my principal plane. Now I can resolve this stress on 3 orthogonal planes, which are they? Plane 1, which is nothing but COB, perpendicular to x1 direction, plane 2, which is nothing but COA, perpendicular to x2 direction, and plane 3, that is plane OAOB, which is perpendicular to x3 direction. So these are 3 planes, and I can resolve this principal stress on these 3 orthogonal planes. How do I do that? So let's say sigma 1 1, which is normal stress, perpendicular to plane 1, acting along x1 direction. I have a shear stress acting on plane 1 along 3 directions, so this will be sigma 1 3, and this will be a shear stress acting on plane 1 along x2 direction, so this becomes sigma 1 2. Similarly, I can write out 2 shear stresses on this plane and 1 normal stress. Similarly, 2 shear stress on this plane and 1 normal stress. Let me write it down here. So in all I have 9 components of stress, which I have mentioned, 3 normal stresses and 3 shear stresses on these 3 orthogonal planes. So let me write it down, that assume that plane ABC is principal plane and sigma is a principal stress. Now I consider that this element is in a static equilibrium. So what you remember the conditions of static equilibrium? So we mentioned that the summation of all forces along x1 direction and equal to 0, summation of all forces along x2 direction must be 0, and summation of all forces along x3 direction must be equal to 0. Here we have seen the stresses are acting. So how you find out what is a force? Let's say summation of all forces along x1 direction. So you can have forces acting or stresses acting along x1 direction are sigma 11, sigma 21, and sigma 31. Basically, these are the forces acting along x1 direction, and or sorry, stresses acting along x1 direction, and I convert them to forces by multiplying the area of that plane on which they are acting. So as seen, or we have used this approach when we dealt with 2D stress state. So I will not be using the same approach here to find out what are the principal stresses. So if we use this approach, you can get a principal stresses in 3D. Okay, so I'm not going to do that because we have used this approach when we dealt with 2D stress state, and moreover the derivation of it is given in mechanical metallurgy book by GE Data. So you can refer this book. So we will take an alternative approach to find out principal stresses, and that approach also we have seen when we studied 2D stress state, that is using finding out eigenvalues and eigenvectors. So we have wrote this matrix equation, and when you want to meet this condition, when you want to satisfy this condition, this either we can be 0 or this must be 0. So we cannot be 0 because we get real values of principal stresses, and that is why we cannot be 0. So the only choice left with us is that the determinant a minus lambda I must be equal to 0. So let me write it down. So you can see that lambda I will make sure that your diagonal elements are subtracted by lambda, okay, and the rest of the components remains the same. And I use this identity, that is sigma 1 2 is equal to sigma 2 1. Let me write it down. So what I use is the condition of static equilibrium, that sigma ij is equal to sigma ji. So I use this, and I try to solve the determinant and equate it to 0. So when I do that, what I get is a cubic equation. Let's look at it. So I get this big cubic equation. So we have get lambda cube minus this term into lambda square, this term into lambda, and then this constant. Now what I do is that I put this sigma 11 plus sigma 22 plus sigma 33 equal to J1, sigma 11 into sigma 22 plus sigma 22 into sigma 33 plus sigma 33 into sigma 11 minus sigma 12 square minus sigma 23 square minus sigma 13 square equal to J2, and sigma 11 into sigma 22 into sigma 33 plus 2 sigma 12 into sigma 23 into sigma 13 minus sigma 11 into sigma 23 square minus sigma 22 into sigma 13 square minus sigma 33 into sigma 12 square is equal to J3. This is what we put, and we can reduce down this big equation into small one, which is I have mentioned over here, that is lambda cube minus J1 into lambda square plus J2 into lambda minus J3 equal to 0. Now this equation is your cubic equation. Okay, so it will have 3 roots, lambda 1, lambda 2, and lambda 3. These are nothing but your eigenvalues, and these eigenvalues are nothing but your principal stresses. Okay, so you have lambda 1, lambda 2, lambda 3 as eigenvalues, and these eigenvalues remain unique for a given state of stress, and therefore any coordinate transformations keeps the state of stress the same. That is what we know, and that's why, like, when lambda 1, lambda 2, lambda 3 will not change, and it implies that we'll get the same cubic equation. Let me explain you what does that mean. So let me write it down. Let me draw a coordinate axis which we have used. So I use x1, x2, x3. Okay, I have a stress state here, something like, let's say I put sigma 1, which is nothing, and then I do some transformation. So you have theta and phi, let's say, and I change it to some coordinate axis with respect to my initial coordinate axis as x1, x2 dash, and x3 dash, and I get something like sigma 1 dash. Okay, state of stress here. So what does this mean? That even if I take this sigma 1 or sigma 1 dash, I will end up in, when I try to solve the determinant, that is A minus lambda I to find out principal stresses, I will end up in this same equation. So to end up in a same equation, irrespective of your transformation, coordinate transformation, what is that should be satisfied here? So you should have J1, J2 and J3 should not change, isn't it? They should remain same irrespective of your coordinate axis. So the conclusion from here is that, let me write it down, J1, J2 and J3, they don't change irrespective of my change in coordinate axis. This is very clear, because if you want to end up in the same cubic equation, because the state of stress remains the same, isn't it? So your J1, J2, J3 should not change, they should not change. So that's why this J1, J2, J3 are called as invariant, and these are three invariants. So if you recollect, let me write it down. When we discussed about 2D stress state, we got two invariants. Okay, I have mentioned you earlier. And when we have 3D stress state, we'll get three invariants. So these are these three invariants. This is what J1, J2 and J3. Now let's look at what this J1, J2 and J3 exactly mean. So let me write it down my stress matrix, and then let me write it down. J1 equal to sigma 11 plus sigma 22 plus sigma 33. So this is nothing but the summation of your diagonal elements. And remember your basic engineering mathematics classes. So you will have this J1 is nothing but the trace of stress matrix. Okay. Now let me write down J2. So this is the term, and I can write this term in another fashion as the sum of determinants. I have three determinants. I can write in the sum of these three determinants. So let's look at this determinant closely. So this is sigma 22, sigma 23, sigma 23 and sigma 33. Now if I look at this determinant with respect to my stress matrix, so these are the components: sigma 22, sigma 23, sigma 23 and sigma 33. So this is nothing but a minor of my sigma 11. So similarly, this determinant is a minor of my sigma 22, and this is a minor of sigma 33. So let me explain it again. So how do we find out a minor? Let me write it down. So let's say minor of sigma 22 I want to find out. So I skip this column, I skip this row, and I will write down other terms like sigma 11, sigma 13, sigma 13 and sigma 33. So this is a minor of sigma 22. So this J2 is nothing but sum of minors of diagonal elements, is what we have seen. This is the sum of the minor of diagonal elements. Now similarly J3, the third invariant, so this is the term, and you can figure it out. This is nothing but a determinant of A. So J1 is the trace of a stress matrix, J2 is the sum of the minor of diagonal elements, and J3 is a determinant A. So all these are invariants, three invariants. Now we have seen these invariants. Now let's come back to our cubic equation to find out what are eigenvalues, lambda 1, lambda 2 and lambda 3. So we have this cubic equation. Now this is very difficult to solve sometimes. So let's say if you know one of the roots, then you can write it in terms of a quadratic equation also. So let's say I know root lambda 1, and I can write this equation in this fashion: lambda minus lambda 1 into quadratic equation equal to 0. Now generally what we do is that when you want to solve the cubic equations like this, we do a substitution. So what substitution we do? We put lambda is equal to t plus 1 by 3 J1. So this J1, we have seen it earlier, it's a first invariant. So let me write it down. So J1, what was? J1 was sigma 11, sigma 22 plus sigma 22 plus sigma 33. That is a trace of my stress matrix. Now when I substitute this equation will be, we can write in terms of t. So we get t cube into constant into t, and then there is this constant equal to 0. So if you look at this equation carefully, it doesn't have any t square term, okay, or square term. So this is called as a depressed cubic. You don't have any square term here. So also I can do one thing. If you see closely the constants here, I mentioned it as a constant, so we'll see whether they are constants or not. So this one is a constant, I call it as P. This one is another constant, I call it as Q. Why it is constant? Because you have J2 and J1, J1, J2 and J3 here. So it's a combination of J1, J2, J3 which remains invariant. So that means we can consider them as a constant. So we have written J1. Let me write J2 will be summation of minus of diagonal elements, isn't it? And J3 is nothing but determinant of A. Okay, so we have seen this in earlier slide. Now I can write this equation in this form: t cube plus pt plus q equal to 0. Now tk, I can find out the roots of this equation using this relation where k takes the value of 0, 1 and 2. So you should be careful that k is starting from 0, 1 and 2. So now I get three roots, t0, t1 and t2. And these three roots I can plug in here to find out what is lambda, okay, or lambda 1, lambda 2 and lambda 3. So we'll get principal stresses. So we can find out the principal stresses, and you'll get a real roots only when this for this equation, when 4p cube plus 27q square is less than 0. We'll definitely get a real roots. Why? Because your stress matrix is symmetric, and that's why you will get a eigenvalues must be real, and that's why principal stresses must be real. So I have solved an example in an Excel sheet. I will share that Excel sheet with you, and which has given a 3D stress state, and from that using this approach we have figured it out what are the eigenvalues that is our principal stresses. Now when we get principal stresses, let's say we get our eigenvalues, let's say lambda 1, lambda 2 and lambda 3. I can consider sigma 1, sigma 2 and sigma 3. So what is that determines sigma 1, sigma 2 and sigma 3? Let's look at. So we have three principal stresses. So which one we consider? Sigma 1 is greater than sigma 2 or greater than sigma 3. So by convention we use that sigma 1 is greater than sigma 2 and is greater than sigma 3. What does that mean? Sigma 1 is the algebraically greatest principal stress, okay, and sigma 3 is the algebraically smallest stress. So let's understand this by taking some examples. So I have three conditions which I have mentioned over here. So in first condition, both are tensile in nature. In second condition, one is tensile, another is compressive, and in third condition, both are compressive. So let me write it down. So this is positive, this is positive, this is positive, this is positive, sorry, this is negative, this is negative, so this is negative, this is negative, this is negative. So this is my sigma 1, this is my sigma 2, this plus it is more than minus 50, so this will be my sigma 1, this will be my sigma 2, minus 80 is less than minus, so this will be my sigma 1 and this will be my sigma 2. So let's take one other example. Let's say I have three principal stresses, 150, minus 200 and 60. So which will be sigma 1? Sigma 1 will be algebraically highest, so this will be sigma 1. Sigma 3 is algebraically lowest, so this will become sigma 3 and this will become my sigma 2. So similar approach we use it for our 2D state stress. Okay. Now let's look at how this sigma 1, sigma 2 and sigma 3 can be represented geometrically. So we have used Mohr's circle to represent 2D stress state. Now we'll see how 3D stress state can be represented using Mohr's circle. So if you recollect construction of Mohr's circle, let's take an example and then try to understand how we can construct a Mohr's circles for 3D stress state. So you have this principal stresses acting on 1, 2 and 3 plane. Let me mark those coordinates x1, x2, x3. So you have sigma 1 equal to 100, sigma 2 equal to 50 and sigma 3 equal to 20 MPa. Now let's revise what we have studied for constructing Mohr circle for 2D stress state. So what is that we have on x-axis and what is that we have on y-axis? So we plot normal stresses on x-axis and we plot shear stresses on y-axis. Let me mark it here. So we have sigma and tau, sigma on x-axis, tau on y-axis. Now here I don't have any shear stresses, so I have only normal stresses and all are in tensile. So I mark this normal stresses. So shear stresses are 0 here, so I have points which are on my x-axis only. So this is sigma 1, this is sigma 2 and this is sigma 3. Now what you do is that you mark or construct a circle between sigma 1 and sigma 2, sigma 2 and sigma 3, and then sigma 1 and sigma 3. So basically you will have 3 circles. Okay. So how you do that? So let's say you get this circle between sigma 1 and sigma 2. You draw a circle. How you do that? Let me write it down for you. So you have radius r1, which is nothing but your sigma 1 minus sigma 2 upon 2, and you have a center for it. So what will be its center? Its center will be sigma 1 plus sigma 2 upon 2. Just revise this, check this, what we have done for 2D stress state. Similar approach we are using it for 3D stress state. So you have h1, you have the center of this circle as sigma 1 plus sigma 2 upon 2, and the radius will be sigma 1 minus sigma 2 upon 2. So with this radius and this location, I draw a circle. Similarly, I draw a circle between sigma 2 and sigma 3. So let me write it down for you. So what will be r1? R2, I should write it as sigma 2 minus sigma 3 upon 2. And what will be H2? H2 will be sigma 2 plus sigma 3 upon 2. Similarly, I can have R3, which is nothing but circle between sigma 1 and sigma 3. So its radius will be sigma 1 minus sigma 3 upon 2. And its center should lie on this coordinate, which is sigma 1 plus sigma 3 upon 2. So this is what will be the H. Now let me draw the third circle between sigma 1 and sigma 3. So this is a blue circle. So now this circumference of sigma 1 and sigma 2, the circle which I have drawn between sigma 1 and sigma 2 represents. So it represents my xy plane. So this is my xy plane bounded by x1 and x2. Similarly, this represents my yz plane, and this blue circle, the circumference of blue circle, represents my xz plane. Now, based on this Mohr circle, we know the principal stresses here. So we want to find out the location of plane of maximum shear. That is what we have done in case of 2D stress state. So you have tau max, which is occurring on between plane sigma 1 and sigma 2, will be at this location. Okay, isn't it? This is the maximum point, the tau max which we get for this green circle. Okay, so what will be the magnitude of tau max? So we have seen that also. Let me write it down that for you. So tau max is nothing but the radius of Mohr circle. The magnitude will be radius of Mohr circle. Okay. So and this tau max will be located. What will be its location? It will be always 45 degrees from principal planes. Okay, 45 degrees from principal planes in reality. Okay, in reality on Mohr circle. On Mohr circle, it will be 2 theta, isn't it? So 2 into 45, that is 90 degrees. Okay, so you can check it. So from this sigma 1, it is 90 degrees, isn't it? Or from sigma 2, it is also 90 degrees. Similarly, let me draw tau max between sigma 2 and sigma 3, which is given by this magnitude, and its location is at this push plane, okay, which is 45 degrees from sigma 2 and sigma 3. Similarly, I can have tau max between sigma 1 and sigma 3, which is nothing, which can be given by the radius of this blue circle, and its location will be 90 degrees from sigma 1 and sigma 3. So this we have studied in 2D stress state in detail, so we have just applied it for 3D stress state. Okay, now someone asks you what is a maximum shear stress experienced when we have given this 2D stress state. So you can 3D stress state. Okay, so what will you answer? So the maximum shear stress is this one. Okay, so you can see that this is the maximum shear stress can be experienced. So this will be tau max on xz plane. So that will be sigma 1 minus sigma 3 upon 2. Now here, if you look at carefully, so you will have maximum shear when sigma 1 is the largest, okay, greatest. Let me write it down. So sigma 1 is the greatest principal stress and sigma 3 is the lowest. So the maximum shear will occur on a plane between sigma 1 and sigma 3. And this is but logical. You can see it here. The maximum shear stress is occurring at this location or at this plane, which is, let me write it down again, which is 45 degrees in reality. Here it is on Mohr circle, it will be 90 degrees, and in reality it will be 45 degrees, which I have mentioned over here. So you have maximum plane of maximum shear lying 90 degrees from sigma 1, which is the largest or the greatest principal stress, and sigma 3, which is the lowest principal stress. So with this, I will stop here.